Welcome back to our third explainer in this series. Today, we're focusing entirely on giving you the ultimate optical blueprint for IGCSE physics lenses. You know, if you've ever felt completely overwhelmed trying to memorize exactly where an image is going to form when you move an object around in front of a lens, well, you're in the right place. By the time we wrap this up, you won't need to rely on rote memorization anymore. We're going to build a geometric toolkit together that makes those ray diagrams absolutely, completely predictable.
Okay, let's take a quick look at today's roadmap. We'll start with the 3 ray rules, move into real versus virtual images, tackle convex image formation, explore magnifiers and illusions, and finally wrap up with correcting human vision. Let's get to it.
Section 1. The 3 ray rules.
So converging, or convex lenses, reliably force light rays into highly predictable paths. To actually find an image, you only ever need to draw 2 of these 3 rays, but you really should know all 3. Rule number 1. A ray traveling parallel to the principal axis is always going to refract perfectly through the focal point on the other side. Rule 2. A ray passing through the focal point on the way in, well, that'll refract out perfectly parallel to the axis. And Rule 3, a ray passing directly through the optical center of the lens just continues straight through. No deviation at all. Honestly, just memorize these 3 lines and you've basically unlocked half the topic.
Now, on the flip side, concave or diverging lenses scatter light outward. So let's see how our rules adapt here. Rule 1. A parallel ray refracts outward, sure, but if you trace a dotted line backward, it looks exactly like it came from the near focal point. Rule 2. A ray heading toward the far focal point gets bent parallel to the axis. And Rule 3, that remains exactly the same, straight through the optical center with 0 deviation. Because the light rays physically spread apart here, our brains are literally forced to trace dotted lines backward just to figure out where the image is.
Moving right along to Section 2, Real versus Virtual Images.
Okay, this is absolutely crucial. The reality divide. Real images happen when light rays physically converge and actually meet each other in space. Because the light is genuinely there, you could place a piece of paper or a cinema screen at that exact spot, and boom, the image is projected right onto it. Also, keep in mind real images are always inverted, meaning upside down. Virtual images, on the other hand, are essentially optical illusions. They form when rays diverge, and our brain extends those diverging rays backwards to a point where they never actually met. You cannot project a virtual image on a screen, but you can see it by looking into the lens. Think about your reflection in a mirror. That's a classic virtual image.
Section 3. Convex image formation. Quick exam pro tip for you before we map out the variables. The examiners are incredibly picky about vocabulary. You absolutely must state if an image is upright or inverted, real or virtual, and crucially, you have to describe its size. Always use the word diminished if the image has shrunk or magnified if it's been enlarged. Don't just say smaller or bigger, okay? Use the proper terms.
Think of this convex master matrix as your literal cheat code. I'd highly recommend visualizing this progression in your head. Just notice how the image shifts as the object gets closer to the lens. When the object is far away, like beyond 2f, the image is real, inverted, and diminished. Now, move it exactly to 2f. The image is still real and inverted, but now it's exactly the same size. Push it a bit closer, between 2f and f, and it becomes magnified. But here's where the real magic happens. When you push the object extremely close, between the focal point and the lens itself, suddenly the whole thing flips. The image becomes virtual, upright, and magnified.
But wait, look closely at that progression. What happens in that tiny split second when the object sits exactly on the focal point, f? Well, here's a classic IGCSE trap for you. When the object is exactly at the focal point, the rays emerge from the lens perfectly parallel to each other. And since parallel lines never meet, not forwards, not backwards, no image forms at all. Definitely keep that in your back pocket for those tricky multiple choice questions.
Section 4. Magnifiers and illusions.
You know, a magnifying glass is actually just a regular old standard convex lens. That's it. But it only works if you use it correctly. By trapping the object closer to the lens than the focal point, the rays passing through the lens diverge. Your eye catches these spreading rays, and your brain traces them backward, essentially tricking you into seeing a massive virtual image behind the lens.
If your exam asks for the nature of an image in a magnifying glass, you literally just need to list these 4 exact properties to secure full marks. It's virtual because the rays don't physically meet. It's upright, which is precisely why the text you're reading isn't suddenly upside down. It's magnified, obviously, and importantly, the image appears on the same side of the lens as the object itself.
This exact same principle of virtual image formation also perfectly explains the apparent depth illusion. Have you ever looked into a swimming pool and thought the bottom looked way closer than it actually is? When light moves from a denser medium, like water, to a less dense medium, like air, it bends away from the normal line. Your brain, which always assumes light travels in a perfect straight line, traces those bent rays backward, and it creates a virtual image of the pool floor that is much, much shallower than the real depth.
Finally, Section 5. Correcting human vision.
Let's start with short-sightedness, or myopia. This happens when a person can see near objects just fine, but distant objects, totally blurry. Why does that happen? Well, usually the eyeball is too long, or the eye's lens is just too powerful. The light rays converge too early, and they meet in front of the retina. To fix this, we strategically place a diverging, or concave lens right in front of the eye. This lens spreads the rays out just a tiny bit before they even hit the eye, which delays their convergence so they land perfectly, crisply, on the retina.
Now for long-sightedness, or hypermetropia, it's the exact opposite situation. The person can see far away clearly, but reading a book is a blurry mess. Here, the eyeball is too short, or the lens is too weak, which causes the rays to try and focus way past the retina. To correct this, we use a converging, or convex lens. This pre-bends the light inward before it even enters the eye, bringing that focal point forward to restore a beautifully sharp image right exactly where we need it on the retina.
If you have to draw this out on your exam, and honestly you probably will, pay close attention. Always remember to meticulously label the retina at the back of the eye, the corrective lens in front, and most importantly, explicitly draw the corrected light paths, showing those rays meeting exactly on the retina. Seriously, if your converging point is even slightly off the retina, the examiner is going to penalize you. And there you have it. You now possess the complete optical blueprint. We've gone through the ray rules, the nature of images, and some pretty cool real-world applications. By just following the lines and really understanding how convex and concave lenses manipulate light, you can conquer any ray diagram the exam throws your way without breaking a sweat.
So if mastering a simple curved piece of glass lets you cure human blindness and literally alter reality, what other invisible forces of the universe are just waiting for you to bend them to your will? Think about that as you practice drawing out those focal points. Physics isn't just about passing a test, it's about understanding the mechanics of the entire universe around you. Grab some paper, get practicing, and I'll see you in the next explainer. Keep learning and stay curious.